So in this presentation, I'm going to cover how Bitcoin mining works. I'll start out with what is mining, and I'll cover what it is and why it exists. And then after that, I'll cover how it works. But before I can cover how it works, I need to explain what a hash function is, because that's like an integral part of how Bitcoin works. Then I'll cover the basics of how it works, and then I'll go through it again, but I'll explain it in a more technical way, so if you're a programmer, you'll find that more interesting. Then after that, I'll start doing some examples, and I'll try and show you how you could actually mine a live block in a very small amount of code. So that's what the presentation is going to be. So I'll get started with what mining is. So what is mining? Well, imagine this is the Bitcoin network, and these are all the computers connected together, running the Bitcoin program, and sharing the same file, which is this blockchain. The way Bitcoin works, if you want to send a Bitcoin to someone, or transfer ownership of a Bitcoin to someone else, the way you do that is you create a transaction with just a little line of data, and then you'll insert that into a node on the network. And then if we didn't have mining, the way this would work was that computer would write it straight to the blockchain, to the shared file, and then what they would do, they would pass on that transaction, that piece of data, onto the nodes they're connected to, and they will write it to their file, and so on, until that transaction has propagated the entire network and written it to their shared file. So that would be a simple way of, having a shared file or shared ledger of transactions. And then when everyone's updated their copy of the file, the ownership then of that Bitcoin has changed from one person to the next person, and that would be a simple transaction. But there's a problem that needs to be solved if you were to do it this way. Let's colour this man in green. What you can do is you can create a transaction to send the Bitcoin to this person and insert it into a node on this side of the network. But what you can do, because it's a network of connected computers, you could create a second transaction that sends the very same Bitcoin to a different person. So you've just inserted two separate transactions into the network trying to spend this same Bitcoin. And you can do this because it's a network. So what will happen from there is these two transactions will start propagating the network, and the computers on this side, as you can see, they have received this red transaction, the second one, but the computers on this side, they've received the green transaction. When this computer here tries to pass on their green transaction to this computer's already received the red transaction spending this Bitcoin, so they would reject it, which is good, but then you still have the problem then of these two conflicting transactions on the network, or basically if you look at the network as a whole, or this file as a whole, who does this Bitcoin belong to now? So if you were to run Bitcoin this way and write transactions directly to the file, you could create this double spend problem. So basically Bitcoin solves this problem of not having conflicting transactions written to the blockchain or to this shared file, and that is what mining is. So the way Bitcoin solves this, and this is really, this solution now is what makes Bitcoin interesting, because we've had this technology before. Yeah, go on. Do you have a question? Okay. Did you miss anything? Okay. So Bitcoin solves this problem of having, writing two conflicting transactions to a shared file. And this is what makes Bitcoin interesting, and this is what the the invention of Bitcoin is. So the way Bitcoin solves this double spend problem is that it gives every computer running the Bitcoin program some temporary memory called the memory pool. So what will happen is you can't stop this double spend attack, but what will happen is the person will insert a transaction into this computer, this green transaction, then they can go over here and do the same, double spend attack again and insert this second red transaction into this computer. But obviously, these two transactions aren't written directly to the file. They get stored in temporary memory first. So again, the same thing happens. Both transactions propagate the network. This one will reject the green one because they have already received the red one. And so there we are. Both transactions on the network, but they're not written to the file yet, so the file is still secure. What will happen then is all of these computers will work to try and get the transactions from their memory pool onto the file. So they're all competing basically to be the first one to get their memory pool transactions added onto the top of the file. So let's say this one is the first one that's able to do it. They add their transactions from their memory pool onto the file, like so. And when they've done that, they will pass on their updated copy of the file to everyone else they're connected to, and they will update their copies. And this node here, because they've got this conflicting green transaction in their memory pool, but they've just received this red transaction spending the same bitcoins, they will kick out this green transaction from their memory pool. So this memory pool is like a waiting area or like a clearinghouse, and they've received this red transaction in the updated file, so they'll kick out this conflicting one, and then this node will pass on the updated copy to these nodes also, and they will do the same thing. They'll kick out any conflicting transactions from their memory pool. So that's how you solve the problem of having two conflicting transactions on the network. You just literally have a waiting area, and all of the nodes compete to try and add their transactions onto the file, like so. And there we are. This person now has the Bitcoin, and so this process of every node competing to try and get their transactions from their memory pool onto the file is called mining, and that's why I'm going to explain how it works now. This, getting these transactions onto here. Is there any questions about that so far?
Not really, but one thing to note here is that every node in the network is not necessarily mining.
Oh yes, that's true. Yeah. I just made a very simple diagram trying to, but yes. So some of these might not be mining. You can just run a node that will relay the blocks and transactions. But in this particular simplified diagram, everyone's trying to mine. But obviously, go on. Yep.
Yeah, let's say we have a node that is not mining. So if it gets a block which has a transaction and a conflicting transaction in the memory pool, it will take it out.
All this relaying of blocks and transactions, a node will do this, but a miner just does this latter part of trying to add the transactions from the memory pool. That is a miner, this part here. But you can be a node, but you don't have to mine. Okay, is that right? Okay, so that's the intro done. So the next part now is explaining what this hash function is, so that then I'll cover how Bitcoin mining works. Right, so a hash function. But a hash function is just like a small computer program that does this, quite useful. But the way it works is you can have some data. So this is letter A and the number 1, and you can insert it into the hash function, and the hash function will basically scramble it and produce a random string of data as a result. And the useful property about a hash function is that you can put the same data into it and it will always spit out the same result. So basically it will scramble it in the same way to produce this random string of data. And this string of data will always be the same size, which is 32 bytes or 64 characters, because there are 2 characters per byte. So if you were to make a tiny adjustment to the data you're putting into the hash function, so from here just got from A1 to A2, just a tiny adjustment, put that in, the result would be completely different. So we've only made a tiny adjustment, but the result of the hash function is wildly different. And again, put A3 into it, tiny adjustment again, but the result is completely different again. And an important part about a hash function as well is that if you don't know what the result is beforehand, there's no way you can predict what A2 is going to spit out. So if you don't know what this already is, then there's no way you can sort of figure out what the result's going to be, which is useful, as we'll come to see in a moment. Also, lastly, even though this looks like it's a random string of data, it's got like the letters F, E, A, basically A, B, C, D, E, and F in there. These can actually be converted into numbers, and that's because we are used to using the decimal format for numbers, which uses the numbers 0 to 9. But you also have a number format called hexadecimal, which is just the same numbers but also with A, B, C, D, E, and F. And they are, when you translate them over, when you convert them over, they just looks like this. So this is called decimal because it uses 10, and deci means 10, I think, in Latin. Then hexadecimal, hexa, like a hexagon, 6 sides, deci, 10, 6, 10, 16. So basically, this is what we use as humans, but computers are very happy to read numbers in hexadecimal format. So basically, with a hash function, you put data in and it spits out a random number as a result. But so if you see like a string like this in hexadecimal format, just remember that it's a random number. Does that make sense? Everything makes sense there? Right, brilliant. So that was a hash function, just a little tool that spits out random data. If I quickly show you, I don't know if you can see this, if you can read the text, but if you can, like, a hash function is available in lots of programming languages. So for example, in PHP, there's a function called hash, and then you can tell it, that's got a bit wrong there, and then you can tell it which hash function you want to use. So SHA-256, that is the one that's used in Bitcoin, which stands for Simple Hashing Algorithm 256, or 256 bits, which is like the size of the result it spits out. And then you can just put the what you want to hash into it. Oh, that's gone wrong. Oh, that's, yeah, echo hash SHA-256 A1. There we are. So that's the result there. So you can use a hash function in any programming language. I've just showed how to use it here in PHP. In Ruby, just for be complete, it's included in the digest library, so you can go put digest SHA-256. Then we want the hexadecimal digest. Digest is just another term for the result that gets spat out from a hash function. So we want to put A1 into there, and there we have the same thing. So hash function is just available in lots of programming languages. Okay, now I'll move on to the basics of how mining works. So I'll just run through, giving a quick example of how this process here of getting the transactions from the memory pool onto the blockchain works. Right, so basics of mining. Here we have the network again, all the transactions in the memory pool. Yep, sorry. Okay, okay. Thanks. Just if it happens again, just let me know, and I'll. So again, we're just going to look inside now this computer. This node here is a miner, so we're going to look inside it and see how it mines the transactions from its memory pool onto its file. Right, so you still there? Hello? Oh, you still? Yeah, okay, right. Yeah, okay, right. So this is looking inside a Bitcoin miner. So this is the memory pool. It's got the red transaction in there. But with a memory pool, you can have much more than one transaction in there. So let's say this memory pool has got, like, quite a few transactions already in there. So what a miner will do, they will create a container called a candidate block, which is just a container for transactions. So what they will do, they will fill this candidate block up with transactions from their memory pool, and like so. And then they will try and add this block of transactions onto the file, onto the blockchain. So how do they get this candidate block that they've built onto the blockchain? Well, the first thing they do, they construct what's called a block header, which is just like a summary of all the data inside the block, all the transactions in the block. So in that block header, you have something called a version, which is like a version number for the block, for the structure of the data. So let's say that's 1. They will also have some information called the previous block, or the previous block hash. And the way that works is, let's say this is the blockchain. This candidate block they're building, it has to build on top of one of these blocks. So what a miner will do is they will include the hash, or the block hash, which is like an ID number for a block of the one they want to build on top of. So like so. So in here, this is the block hash for this block. So this just says which block they want to build on top of, because every miner basically wants to build onto the top of the blockchain. Merkle root. Now a Merkle root is just basically if you hash all the transaction IDs together over and over again, you'll end up with a single hash at the end, and this is called a Merkle root, like so. And basically this is like a fingerprint, like a digital fingerprint that summarizes all of the transactions in the block. So again, this block header, it's like creates a unique fingerprint for all the data in the block, but using a lot less data than all of the transaction data combined.
So maybe if you can, speak a little about the Merkle root, because I've not really heard too much about it. Are you like hashing like every other transaction together and then hashing those results? It looks like that.
I'm going to actually cover that in the next technical part, but just for now, as long as it makes sense, that this Merkle root provides you with like a unique short summary of all the transactions in the block. Okay, and I'll cover how that works and why a Merkle root is used in a moment. But yeah, good question. Anyway, so there we have the block header. I haven't covered all the block header data, but this is the most important stuff. So there we have a block header. The next step then is to put this block header data into a hash function, into the SHA-256 hash function, and then that will produce a random number as a result, and this is called the block hash, a block hash. Any questions so far? Okay, and so that's all well and good, but why would a miner do this? Or how does this help to get the block mined onto the blockchain? Well, if this block hash, the result of this putting the block header into the hash function, produces a block hash that is below a target value, like so. So let's say this is the current target value, which is a number, which is like a number internal to every Bitcoin node. They all calculate their own. It's like a shared target value that is calculated in sync with every other node. If they can get their block hash to be below this, then the block will get added onto the blockchain, and the block is solved basically. So far with this first attempt, this number here, as you can see, this target value starts with a certain number of zeros, but this one is obviously a bigger number than that, so it's not below the target. So this first attempt at trying to add this block onto the blockchain has failed, like so. So what happens then is a miner doesn't give up, in the block header, there's space. There's an extra field called the nonce, which stands for a number used once. And this is like sort of like an open field that a miner is free to put their own number in or data in. So what that means is, if this first attempt of the block header fails, they can change the nonce value or change the data in the nonce. So for example, their first attempt they might have had the number 0 in there. Then if that fails, they'll change the nonce and then push the block header through the hash function again. And because even though we've only made a small adjustment, like I showed you earlier with a hash function, small adjustments can produce completely different results. So a miner basically will construct a block header and keep changing this nonce value and hoping that the result will produce a block hash below the target value. So literally, a miner creates a block header, adds a nonce to the end, and if it doesn't work, they'll keep incrementing it, hoping to get a low enough block hash. Eventually, if they're lucky, this is just pure randomness and pure luck. They might be able to guess a nonce that works, that'll produce a block hash below the target. So here, this particular very high nonce has produced a successful block hash result. So there we are. So what will happen then is this node will add that block onto their blockchain, and they will pass on this candidate block or this solved candidate block onto all the nodes they're connected to. They will check it and verify it to make sure that the block header, produces a target below a block hash below the target. They'll add it to the file, kick out any conflicting transactions that are included in that block, and then pass on the block like so, and they'll do the same thing. So that's how mining works on a basic level.
So I had a quick question here.
Yep.
So you're saying that the target value is each node has its own value for the target value, right? So I've never thought of this, but there is a possibility that I mine a block which is below my target value, and I give it to my neighboring nodes, and maybe the target value has changed, or for some reason the other nodes don't have the same target value. Is that a possibility, and how does that?
Yeah, no, I understand the question. I think I explained the target not great. Let me find out if I right, the target the target, I'll explain it now. Basically, the target is there so that every 10 minutes a new block will be mined. But if more computers are hashing a lot faster, then a block is likely to be mined in under 10 minutes. So this target value obviously moves up and down, so that a new block is mined every 10 minutes. So the target for the very first block, when you first start running Bitcoin, the very first block, it was hard coded in at this value. And then after every 2016 blocks, or roughly every 2 weeks, what will happen is every node, they will look at the time it took for all the last 2016 blocks to be mined. So the expected time for that is obviously 20,160. But if the actual time for all those blocks to be mined was less than that, then the target will adjust. So the target will adjust by this ratio. So there we are. So this ratio, because it was mined, all the blocks are mined faster, is 0.9. And so this target, as you can see, will adjust downwards. So every single node, when they receive a new block, after every 2016 blocks, they will all do this exact same calculation. So every node started with this value, but if everyone's on the same block, then everyone will have calculated the same target. So it's basically everyone shares the same target. They all calculate it themselves, but because they're receiving all the same blocks, they'll calculate, everyone will have the same target value. So not everyone has different target values, everyone has the same calculated target. So again, this happens every 2016 blocks. The same thing happens. How long did they take? What's the ratio? Okay, that was mined faster. Move it down again, like so. Okay. So that's how the target works. Also, up until now, just to clarify, I've referred to this blockchain as a shared file. The shared file is a blockchain. Basically, the shared file is full of transactions, but because the transactions are added in blocks, like so, the file is called the blockchain because each block builds on top of each other. So with Bitcoin, it is a shared file, and this shared file is called the blockchain. So if I just update the diagram, you can think of the shared file as, just blocks built on top of each other. Finally, why would anyone mine? What's the incentive for a miner to use all this hashing power on their computer to try and mine the transactions from the memory pool onto the blockchain? Well, every time a miner mines a block or is successful in mining a block, they will receive what's called a block reward. It starts out at 50, but it halves roughly every 4 years. So that's the incentive to mine a block. And the way a miner receives this block reward, when they construct the candidate block, the very first transaction is reserved for them to put there. So a miner will put their own transaction at the top. They're called a coin-based transaction. And this is a special transaction because it allows them to send themselves a set amount of bitcoins that had not previously existed. So if this block does get mined onto the blockchain, they will be able to receive new bitcoins thanks to this coin-based transaction that they put there. They put their sort of Bitcoin address in here so that they can receive the block reward. So just to summarize the basics of mining, a miner will get the transactions from the memory pool, then they'll put their Coinbase transaction at the top so they can receive a block reward if they're successful in mining this block onto the blockchain. Then they'll create a block header, then they'll hash it, hope that it's below the target value. If it's not, they'll keep adjusting the nonce over and over again and if they're lucky, they'll find a nonce before anyone else that produces a block hash that is below the target, and then they have mined the block, like so. Does that make sense? Okay. I think what I'll do now, I'll just show you a little mining simulator. A little mining simulator. So this is what a Bitcoin miner might look like if you under the hood, basically. So what they'll do, they'll go into their memory pool, they'll get the transactions from their memory pool. This mining simulator is mining a block that's already been mined. So this is a long time ago. There's only 13 transactions in the memory pool. There's obviously a lot more in there now. What they'll do then, they'll construct the block header. I haven't covered these last two bits of the block header yet, but don't worry, I'll cover them in a moment. But obviously this data refers to the previous block, has the Merkle root, the version number. And then what they'll do, they will squish all of that data together into one line of data, and I've left some space here for the nonce. So this is the block header data. This is the target, and then what a miner will do now is they will take this block header and put a nonce in there, keep incrementing it, and these are the results. If you can see now, this is a very slow miner. So as you can see, these are the nonce values on the left, and these are the different hash values that block header is producing.
Okay, so this is so when you created that string on top, that did not include the transactions. It included only the header.
Yes.
So okay.
Yes. Also, what the transactions, I suppose, are included in this Merkle root. This Merkle, this Merkle root is the summary of all the transactions. This sort of refers to all the transactions in the block. Here also, here's the code for this miner. It just basically just mines a block header. It just hashes a block header. I've made this code available on the website. I'll give you a link to it in a moment. But for this particular miner, I know what the successful hash value. Right there. Let's grab this. There we are. So let's reduce this down by 100. So if I start this again, I've increased the starting nonce value. So again, this is the block header. The nonce is going to start not from 0 this time, but a much higher number. And if I let it run now, hopefully after about 100, it'll stop when it finds a block hash below the target value. There we are. Don't know if you can see this. Right there. So there we are. The block has been mined. So this particular block hash, purely random and just pure luck, produced a block hash starting with this many zeros, and that was below the target. And so that's all a miner does, is they just grab a block header, change the nonce, hash as fast as they can. Does that make sense? Okay. If I'll put these links at the end. But if you go on the website onto learnmeabitcoin.com/code, I've put the mining simulator code up here. I've made it it's written in Ruby, just because I think it's a simple and easy to read language, similar to Python. I've tried to make this as simple as possible. So if you want to start, hashing your own block headers, you can. So on the website as well, on Learn Me Bitcoin, if you go onto the browser, you'll be able to see these latest blocks, and these are the block headers. And if you click on serialized, it'll show you the serialized code, and if you were to hash this, it would produce this block header. And so this is a candidate block basically, and it's trying to do the same thing. Right. So
just curious. I mean, this is this running off like a machine that you have? I mean, Learn Me a Bitcoin. Is this live?
Yeah, this is live. Yeah. So this is a live candidate block. These are all live transactions. So it's all on the browser. Let me go back. Right. Okay. Okay. So that's the basics. Intro. Right. So that was the basics of. Now I'll go on to the technical. Basically, I'm going to run through the exact same thing, but do it in a technical way. So if you're interested in programming and actually mining a block, this is basically the same stuff, just from a programmer's perspective. Right. So again, just repetition. Going to repeat the same stuff. Same thing. Memory pool. Grab the transactions to memory pool. Fill up your block. Then there we are. This is the candidate block. Then you'll put your Coinbase transaction at the top. The first transaction in a block is always a Coinbase transaction that a miner has put there. And so that allows you to claim the block reward, which is currently 12.5 Bitcoins. The reason you would put the Coinbase transaction at the top of the block after selecting all these transactions is because each of these transactions will have a fee, and through your Coinbase transaction you can collect all of these fees. So instead of the Coinbase transaction just receiving the 12.5 block reward, you'll be able to send yourself something like 13 or more, maybe, depending on how much the fees are worth. Depends how much you can send yourself in this Coinbase transaction.
Okay, so the Coinbase transaction includes the fees.
Yes.
It's not only the mining reward. Okay.
Yeah. So basically, you have the base level, which is the block reward, but then you can send yourself however much all these fees from each transaction.
Mm-hmm. So this means that miners will tend to pick transactions with a higher
Exactly.
fee.
Yes. So there we are. We've got those transactions.
One more question on that. So I remember seeing a graph where it showed me like on the left the fees, and on the right like kind of how much time it will take to mine that block.
Yeah.
So does this mean that, you know, if we put a very, very low fee, is it ever possible that our transaction will never get never be part of a block? Is that ever possible in your experience?
Yeah.
Or
What can happen is, so say you make a transaction, it'll go into the memory pool first. If there's a lot of transactions in the memory pool, then you basically your transaction is competing with all these other transactions for space in a block. Because a block, it's the way a block is. It used to be 1 megabytes worth of transactions. It's roughly about 1.7 now. It uses a different metric called weight, but I'm not going to cover that just now. But what will happen is, say you put such a low fee on there that it doesn't make it into the blocks, it's still hanging around in the memory pool. If your transaction stays in the memory pool for longer than 72 hours, on average, your transaction will just get kicked out of the memory pool. So if you put a very low transaction fee on a transaction, there's a chance that it will never make it into a candidate block, or even or onto the blockchain.
right. So again, in your experience, what's like the bare minimum? Let's say if I want to send like $5 to someone, or buy a coffee, like $3. What's the minimum fee that I have to pay? I mean,
I think wallets generally tend to help you out with that, but I don't think they're great at it. But one way, what I would do is I would look at this candidate block, and transactions in general are ordered in a candidate block from highest to lowest fees, not strictly, but I would head towards the bottom of this candidate block and have a look at each of the fees on them, and you can just basically add a fee that's greater than the lowest fees. Yeah, exactly. That's a rough. I mean, that's like the simplest way to do it, in my opinion. So, yeah.
So again, this is per byte. I think when you hovered over, so fee per byte. So this is so the average byte size of a transaction. Is that what this guy is saying?
So, so this is a transaction, and this takes up space in the block. So then you set a fee on it, but you basically pay in for each individual byte. So the bigger the transaction is in data wise, the more of a higher of a fee you want to put on it to give you, because a miner, they will select transactions based on fee per byte. So basically, which transactions are giving them the most fee for the space they're going to take up in the candidate block. Okay. So again, just going to run through mining again. Put your Coinbase transaction at the top. Then you construct the block header. Same again. You have a version number. This is an old block. The version number was 1. The way version numbers work now is different to how it used to be. They can be used for voting. I'm not going to cover that just now. I'm just going to run through simple block header. Then you have the previous block. Same again. Just refer to the block you want to build on top of, which is basically the tip of the blockchain. Then you have the Merkle root. So the way that works is you have all the transactions in the block. I'm just moving these to the side just for illustration purposes. What you do, you just run through every single pair of transactions and you hash them together. So remember the hash function? You basically line these up. So 1 and 2, just line them up together and hash them together, and that'll produce a digest or hash result. And you do that for every single pair of transactions in the block. If you end up with a transaction on its own that doesn't have a pair, all you do is you just hash it with itself. And then that's the first round done. You have these 4 hashes from all these pairs. Then you just run through again, hash them all together, hash each pair together, and you keep going on until you'll end up with a single hash result called the Merkle root. Now, the question is, why, if you want to create a summary of all the transactions in the block. You're hashing the transaction IDs here together, by the way. But if you want to create a summary or a fingerprint for all the transactions in the block, why wouldn't you just hash them all together like this in a more simple way? Why would you do it in this more elaborate tree structure? The reason for that is, say you were given a Merkle root, and you want to check if this transaction ID is present in this block. The only way you could check it would be to take all of the other transaction IDs. You would need all the other ones, including the one you want to check, and then hash them together to get the Merkle root. To get the hash, sorry. But with a Merkle root, say you want to check the presence of this hash here, all you actually need is you need this one to create this one, and then if you got that one, and then all you need is that one, and then you can create that one, and then all you need then is this one up here, and that will give you this Merkle root. So the other one needed, what was it, 1, 2, 3, 4, 5, 7, 6 transaction IDs, but this one only needed 3. So obviously it doesn't look like a massive improvement, but this is just a simple block. If this was a lot longer block with thousands of transactions, then you're needing a lot less transaction IDs to check the presence of a single transaction. I've not done this myself, but apparently this is useful and efficient to do it this way. So that's why we have this tree structure for hashing, because it saves on checking for the presence of transactions in a block.
Sure. Just one question. When you say that we hash like 2 transactions, you're saying that we just concatenate them and hash, do a SHA 256?
Yeah, exactly. You just concatenate the transaction IDs.
Which are basically the hashes of the transaction.
Yeah, so you basically hash transaction data to give you a transaction ID, and then so there we go. That's the Merkle root. Time, also in the block header, you have something called, well, you just have the time, which is a timestamp, like so. But you don't, the way the time is encoded in the block header is using Unix time, which is the number of seconds since the 1st January 1970. So this block's timestamp in sort of a human representation is 12th of May 2011, but in Unix time that would be this many seconds. A quick note on the time, these don't have to be accurate, they just have to be between a certain minimum and maximum value. So the minimum value you can set as the time for your block header is the median time of the last 11 blocks, or basically the time set that's been the time in the block header of the 6th block down. So you can't have a time any lower than that. That's the minimum bound. And then the maximum, the maximum, basically your node has its own time. When you run it, it just uses your computer's time. And then when other nodes connect to you, they will send you what their time is on their computer. And so your node will keep track of the difference between all of the times of the nodes you're connected to. And if you put them in order and you take the median time of all the nodes you're connected to, that's called the network average time. So the maximum value of this time is the network average time plus 2 hours. So
can you repeat this part like quickly? I mean, I just got a little confused. So why is this time used, and is this the time to mine a block or something? I mean,
no. This time. I think this is probably a bit unnecessary for me to explain. Basically, the time is just you just stick the current time of your computer in the block header, but it's not. It doesn't have to be precise. So basically, it just has to be between 2 certain values. As long as it's greater than the time of the 6th block down, or the median time of the last 11 blocks. It can't be any lower than that, because if you were to put a time lower than that, then it would get rejected by the nodes you're sending it to. And also the maximum time is basically the current time plus 2 hours. But we used network average time is used, which is just the average time of all the nodes that are connected to you. So don't worry about that. But it's basically, all I'm saying is the time can be roughly an hour behind or 2 hours ahead. So it's not really so if a block comes through and it has a time like before or ahead of like a different block, it doesn't really matter. It has this sort of flexible sort of upper and lower boundary. All right, so that's the time. Bits. Remember the target. Bits is just a compact representation of the target. So instead of putting the current target, the entire target in the block header, what you do is you just grab the first 3 significant bytes, or the first 6 significant characters after the leading zeros, and then you put that there, and then you just grab the offset, so how far these 3 bytes are from the right, and they are 26 bytes from the right here, or in hexadecimal 26 is 1A, so you just put that at the start there. So bits is just this compact representation of the target. Then that's it. Then you just have the nonce, and you can set that to 0. And so this is all the basic data now for the block header. Does all these fields make sense? Each part? Okay, good. So now we've got all the fields ready to be mined. We just have to get all the data into the correct format. So this is just a bit of programming just to make sure everything's in the right order and format. Each field should be in hexadecimal. Put it all into hexadecimal. So 1 is 1 in hexadecimal, so this isn't going to change. But you just go through every single field, making sure that it's all hexadecimal. So these 2 are hexadecimal. The time, this is in decimal at the moment, so we just convert that to hexadecimal, and you do the same for every other field. Secondly, each field must be a fixed number of bytes. So this has only got 1 character in here, but the version field is 4 bytes. So if we were to convert that into 4 bytes, it looks like this. So 1 byte is 2 characters. So 00, that's 1 byte, and there are 4 bytes in the version. Then you just go through every single field, putting it into the correct size. So this is already 32 bytes. That's already 32 bytes. The time's going to be 4 bytes. It's already 4 bits. Same again for the nonce. Then that's 4 bytes as well. So just for each field, make sure that you've padded it out with the right number of bytes. So this basically means that when a computer can read through each individual field easily. So that's all the data in the right format and the right field size. Lastly, the only slightly frustrating thing with Bitcoin is that when you send data to other nodes across the wire, you have to send the data in reverse byte order, which is called network byte order. So obviously we've got all this in human readable byte order, but when you hash and work with Bitcoin data, it has to be in reverse byte order. So you just go through every single field and put it into network byte order, which is just reversing each byte. So that's something that, well, it tripped me up when I first started mining. I was trying to hash these block headers, and I was like, why am I not getting the same results? It's because you want to get everything in network byte order. Just to show you, I've made like a little quick script. So reverse bytes. So if I put the A, B, C, D, E, F, 1, 2, 3, 4. The way that works is reverse byte order. You just split it all into each individual byte. So 1 byte is 2 characters, and then you just reverse the order of the bytes, and that gives you that. So that's how it works. So you're not just reversing the string, you are reversing each byte.
So this might be a basic question, but 2 characters is 1 byte?
Yes, yeah. That's just something I've learned.
I'm just looking at the C++ I've not done C++ in a long time. So character type size is 1 byte.
Yeah, no, I don't know that much deep about computer science. But all I know is, yeah, I'm doing this from more of like a top-down sort of level. I've just learned that 2 characters translates as 1 byte. So, yeah. So there we are. Now we've got all the data finally in the right order. All you do then, you just concatenate each individual field together like that. So this is the block header. Now it's ready to put into the hash function. As I mentioned, SHA-256, simple hashing algorithm, 256 is used. But in Bitcoin, everything gets hashed twice. It's just the way it was designed. I don't think it provides any massive benefits. It's just the way that Bitcoin hashes things. So you just put this into hash function, spits out a result, and then spits out. Then you hash the result to get you another result, and that's the final hash. Quick note: when you hash things in Bitcoin, this is in hexadecimal, but you convert it into binary first. So you put binary data into the hashing function. And then that'll spit out a binary result. Then you put the binary result into the second hashing function. That'll spit out a second binary digest. And then when you convert that second digest back into hexadecimal, that'll give you the block hash. But obviously this is in reverse network byte order again. So if you reverse it, then that's in the more human format. So if you were to compare this to the target, you want to make sure you want to reverse it back into non-network byte order. so there we go. So this, I've only covered these things because they just trip you up. I mean, getting the fields is quite simple, but then getting everything into the right order, then converting it to binary, and then switching it back again, that's what'll trip you up if you're trying to mine a block header or hash a block header for yourself.
Right, so this was the block header on the left, which already had the fields in reverse network order, right?
Yes.
Okay, then you do a double hash of that, and you convert it to hex, and you converted that again in reverse byte order?
I didn't. I reversed it. I reversed it back. Okay. And
this is how, this is like if you mine the block, this is the hash that you would send on to the network. Is that let's say that you end up mining a block, and let's say you get a nuance that is like below a target value. What do you do next?
I mean, okay, I think I cover that now. I think so. Okay, you don't actually send the block hash. You just send basically the block header and the transactions. So okay, but I don't think you have to, if you're programming, you might not have to reverse it. This is just so I can display the results correctly in a sort of a human way. So again, now like a miner, you just change the nonce. Now I'm incrementing it from 0, 1, 2, 3, 4, 5, and so on. So there we are. Obviously this is in network byte order, and so on. Eventually you'll get a hash that's below the target if you're lucky. Then that's mined. So when you mine the actual block, so this is done now. So this is a successful block header. So if you send this block header to anyone else, they can hash it for themselves and they get the same result. I think that's what they call proof of work, because you can just send this block header to anyone and they can prove for themselves that the hash is below the target. So what you do then is you send this block to all the nodes you're connected to, and what you're actually sending them is all of the transaction data concatenated together for each transaction. Before that, you put like a little transaction counter, which is just a byte. It's a very, very variable sized byte. I haven't covered it, but it's on the website. Just tells you how many transactions are in the block, and then before that you have the block header. So this is what gets sent to all the nodes. So you don't have to send the block hash because they can calculate it for themselves. So that's how mining works. What I thought I would do now is try and show you how you could mine a actual live block. So yeah, right. So if you run a Bitcoin node, you have the Bitcoin CLI command, which allows you to ask the Bitcoin node questions, and one of them you can ask them is to get block template. So what that will do, that will take your current memory pool and gather the highest value transactions that would fill up a block and give them to you. So this is showing me all of the transactions that would make a candidate block. So let me just move this down. Sorry. If I just quickly examine the information inside here, if you use Bitcoin CLI help get block template, that will show you all the fields. That will give you all the fields that it'll produce. But if I just quickly, what we want to see basically to mine a block is to create a block header from all these transactions. So Bitcoin CLI get block template, and I'm going to use grep just to search for the fields that we want. I'm using RG, which is a variant of grep, and so we want to find, we want to have a version number, we want the previous block, then we want the Merkle root, then we want time, then bits, then there's a nonce, but we're going to provide our own nonce, so we don't need that. So looking at the, I spelled that wrong. There we are. So looking at the results of get block template, it's given us the version, the previous block hash. It's also given us the time, current time, and bits. So let's change that to current time. So what it's not given us is a Merkle root. For some, I don't know why it's not, but what you can do, what it is giving you is this is just a JSON parser. It is giving you a list of transactions, and it is giving you all the transaction IDs. So if we just go through each one and say, give us the transaction IDs, need to put that in quotes. There we are. So these are all the transaction IDs in this candidate block. So now we've got all those transaction IDs, we just need to create our own Merkle root for them. So luckily I've written my own script that will take in a list of transactions and create a Merkle root from them. I've made this available on the website. I'll show it in a moment. So if I just do that, there we have a Merkle root. So now we've got all the data we need to mine a block, well, or basically to construct a block header. So if you just bear with me for 5 minutes, I'm going to go through each field, and yeah, so first of all, we need to get the version. Oh, that's done wrong. Take that out. So there we are, using get block template. This is the current version. Like I said, they've changed a bit. So they've been used for voting, so this is why it's a very high number, but I'm not going to explain it now, just take it as it is. So this is the version number, but obviously it's in decimal, so we need to convert that into hexadecimal first. So there we are, and then now it's in hexadecimal. This is already 4 bytes, so I just swap the byte order or swap the endianness, because sometimes the byte order is referred to as endianness. So there we are. So this is the version all set up and ready to go. So I'll just trim the end off that because I'm going to concatenate it all together. So if I save this as a variable, there we have. So I'll just echo that out to check. So that's the version done. So next up, after the version, is the version previous block. So previous block hash. So this is the block hash for the previous block. Let me just trim off the quotes, and then it's already in hexadecimal, it's already 32 bytes, so what I need to do is sort the byte order or put it into little endian. So there we are, and then I can save this then as the previous block variable. Next up then is the Merkle root. Obviously we don't get a Merkle root from the get block template command, but what it does give us is the list of transactions, and for each of those it'll give us a transaction ID. Oops, oh, well, I just lost that. Oh, there it is. So there we go, and from these I can get the Merkle root. There we are, and then it's already in hexadecimal, it's already in 32 bytes. I just need to sort the byte order again. So there we are, I'll save that as a variable, Merkle root. I'm nearly there. I know it's a bit laborious, but so that's, yeah. So version, previous block, Merkle root, then we have the time. For some reason, even though the get block template doesn't give you the Merkle root, it does give you the current time on your computer. Or actually no, it gives you a valid time. I'm not sure if this is I don't know, but this is definitely a valid time. But what you could do, if you don't want to use that, if you don't want to use the get block template time, you can just use the date function from a programming language. So if you just, this gives you the number of seconds in Unix time, so if I just use that, just need to get it into hexadecimal, like so. 1, 2, 3, 4, 5, 6, 7. So that's already 4 bytes. Then we convert it to reverse byte order. There we are. So there it is. That's the time ready. Just trim the end off, and that's the time done. Lastly, bits, which is the compact version of the target. There it is. Just trim off the quotes and then put it into reverse byte order. And there it is. So now we've got all the basic block header data ready in the right format. So if I just construct the block header from each of those individual fields, that is the version, the previous block, the Merkle root, then time, and then bits. So just check what that looks like. There it is. There's our block header, and so all we haven't put there now is the nonce. So if we wanted to mine this, we just need to create a loop that will keep hashing this block header, and we'll adjust the nonce, increment it with every attempt. So the nonce will look like, we'll start off with 0, but obviously we need to get this in the right format, so we need to convert that to
hexadecimal.
Sorry, thank you. Then it needs to, so like so. But obviously this needs to be 4 bytes in length, so I made a little function that will just make sure it's the right size, and then convert the swap endian. Obviously it's not very interesting because I've used the number 0, but if I was to use like a much higher nonce value like that, then like so, it's prepared it for me. So I'm not going to append this to it yet. What I'm going to do, I'm going to create a loop. So while true, do, you want to, oh wait there, before that I want to set a variable to an incremented variable ready. So while true, do, we want to create the nonce, which is going to be, like I just showed you, echo I, then we want to get it in hexadecimal, 4 byte field size, swap endian, trim off the end. So that's the nonce done. Then our attempt at trying to mine the block will be just the block header we created plus the nonce at the end. And then what we want to do is we want to hash that all together. So I've made a little function that will hash for me called hash256, because this is just the double hash, converts it to binary, then double hashes it. We want to hash256 the attempt, and after every attempt we want to increment the nonce. So let I plus plus, so just increment the nonce from this number here, actually, and then done. So hopefully this will work. There we are. So now this is hashing very slowly a block header, the current block header. Obviously it's very slow and it took me a long time, but this is actually trying to mine a block. So if that was lucky, what you'd probably do, you'd have some code in there that would stop when you
if it reaches the target.
Yeah. And then what you do then, there's a function Bitcoin CLI called submit block, and you would just submit the header, the transaction count, and all the transaction data. So if you constructed a successful block header, you would send that to all the nodes you're connected to, and you'd do that using the submit block Bitcoin CLI command.
Is there a way to get the target value from the Bitcoin CLI?
Yeah, so I think it's included in Bitcoin CLI get block template. Yeah, so I think it's target.
Oh, it's there in the block template.
Yeah, so there it is. So this is the current target. So you could grab that target and then stick that somewhere into the for loop. Yeah, but obviously that hashing there is very, very slow.
I totally get that.
Yeah, you'd probably want to do that in a single programming language. This is just on Bash, just for quick sort of illustration purposes. But that just goes to show like how simple mining is really. The hardest part is just getting the data in the right order. But after that, it's you just increment a nonce and hash it, and hope you get a lucky result. I think, yeah, so that's everything I wanted to explain about how mining works. That's all the technical stuff, but obviously it's probably a lot simpler than it's made out to be. On the website, I've made all this code available, so each of those little hexadecimal converters and decimal converters and the swap endianness, they're all here. There's a Merkle root function on here written in PHP. It's not the prettiest, but it will take a list of transaction IDs and create a Merkle root for you. I might not want to use it in production, might want to use a different library. I'm sure there's loads of Bitcoin libraries out there with their own Merkle root functions for you to use. Is there any questions about that sort of mining process?
No, I mean this was really awesome. Great, thanks a lot. Just curious, any experience with those heavy duty miners?
No, I've not actually mined myself, because like we said, like it's so inefficient to mine on your laptop. If you wanted to mine now, it's not a hobby thing. You have to sort of buy a professional mining rig and run it like a proper business, which is a shame because that takes mining out of the hands of the average person then. So so I think if you want to get into mining, you would have to really commit to it. It's not just right, gone. Yep.
Right. Even those guys would be doing, like at a fundamental level, they would be doing the same thing, right? Just faster.
Yeah, so they're just doing the exact same thing, constructing a block header and just hashing it as fast as you can. Like this whole construction of the block header is simple and takes an absolute fraction of a second to do. And then the whole mining, then the whole meat of mining is hashing as fast as possible. Don't think I've missed anything. I think I've covered everything I wanted to. Sorry, I know that was a bit probably repetitive in parts.
No. This was a great explanation again. Yeah, thanks a lot for this.
But I think if you're starting out with Bitcoin, one of the best ways to learn, I think, is to try and mine your own block header. I think it's quite simple to do, and I think mining is one of the sort of first fundamental parts of how Bitcoin works. So if you can figure out how to mine a block header or hash a block header, that's a great stepping stone. That'll give you the tools then to figure out about all the hexadecimal and network byte order, and how to hash. And then you can take those tools then and use them in other parts of Bitcoin, like in, with transactions and all that. So this would be my first place to start if you were to try coding with Bitcoin. I mean, you obviously probably not going to set up your miner, but as a sort of learning experience, this is a great place to start. So yeah, if you want to browse block headers, just go into Lumia Bitcoin. This is the blockchain, and you can browse through each individual block and see all the different block headers and test for yourself that you can get the same block hash results.
Nice.
Yep. So thank you very much for that. That was good to do.
Thanks.
No worries. So yeah.